Swayam Prabha. Digital India. Educated India.
But all of this is well and good, provided we know that V upper bar is equal to V lower bar, and that condition, the if there, is irritating, because it tells you all of this nice story works provided V upper bar is equal to V lower bar, and we already have seen an example where where the two are not equal. Okay, so question then becomes, okay, how can you resolve this? And this is where we basically need a next new idea. You need a new idea, you need a new way to think about the strategic situation. Okay. All this reasoning is so far is good, but we have sort of limited ourselves to a particular way of viewing the options at hand, which is that a player has to play a particular row or a particular column. If you think of essentially the strategies that players are exposed to in a game, right, the strategies that they have in a game, in many cases these strategies can be thought of as let's say, suppose a general wants to decide, which of his, he has to decide whether he wants to take this route or that route. That is sort of one kind of way of visualizing the strategy. Instead of saying that I want to, should I go to this route or should I go to that route, instead of having that sort of dilemma, a general might also ask, okay, if I have 1000 troops, how many should I send to this route and how many should I send to that route? Right. So, many times the kind of strategies that we have with us can be interpreted as something as a set of options on such that we don't have to pick only one of those options, but rather we can decide that how much of our resources are to be allocated to each option. Okay. So, for example, so in the case of the general, he has to decide, okay, I have 1000 troops, maybe I send 300 here and 700 here. Okay. Or if you are a fund manager, you have 1 lakh rupees, maybe I put 25,000 in this project and 75,000 in that project. Okay. So, this way, once you start thinking about it this way, then the options that a player has are not just merely to commit to a particular row or a column, but rather to decide the extent of commitment to each row or column. Alright. Now, this extent of commitment can be thought of in many different ways. One is that, as I said, is a resource allocation. So, you can think, okay, how much resources am I devoting to each option? The other way is to say, well, what I am going to do is I am going to pick a row or a column at random. Okay, and I am going to pick it at random, but I am going to choose very wisely the probability with which I am going to be choosing each of my choices. Alright. This now expands the strategy space. So, now you are not just picking a particular row or a particular column as a player. What you are actually doing is picking every row essentially with some probability, and what you have to decide is the probabilities that you are going to assign to each row or each column. Right. So, this is what is called a mixed strategy. Okay. A mixed strategy is basically a randomized choice of a pure strategy. So, this is one way of interpreting it, but this is mathematically this is good enough. So, we will just use this description. It is a randomized choice of a pure strategy. What is a pure strategy? Whatever we have, the strategies we were talking of so far, they are what are called, we will call them pure strategies. Pure strategies are definite choices of rows or columns. Mixed strategies are randomized choices on top of pure strategies. Okay. So, these pure strategies are what rows and columns, and a randomized choice of the same is what is called a mixed strategy. So, formally a mixed strategy is a probability distribution on the space of pure strategies. Or equivalently, the space of pure strategies, equivalently a random variable that takes values in the set of So, mixed strategy is just like pure strategies are for each player, the mixed strategy is also for each player. So, each player now has to make a randomized choice over his set of pure strategies. Okay. So, the probability with which you play, with which the player plays is the choice that he has to now make. Okay. So, it's when many people use this word randomized in a kind of loose way. Many people use the word randomized in a kind of loose way, where when they say pick something at random, they actually mean pick it uniformly at random. Okay, everything with equal probability, but that's not what we mean here. By random, we mean with a probability distribution, and the probability distribution has to be chosen with in a strategic way. Is this clear? Okay, all right. So, then in this case, now can you tell me mathematically what would be the probability distribution for the row player? So, the row player, the pure strategies for the row player, the pure strategies are the rows. Okay, and suppose there are m rows. So, m rows suppose. Then what are his what is a mixed strategy for the row player? A mixed strategy for the row player is now a probability distribution on this set of m rows, right. So, how do I describe that? So, I need to tell you a probability with which I am going to choose every row. Okay. So, let's write it like this. Let yi be the probability of choosing row I, probability of choosing row I. Okay. Now, if this is the probability of choosing row I, now what must these yi's satisfy? How many yi's are there? There are m of them. Okay. What should these yi's satisfy? Yeah. So, because this is a probability distribution, it has to satisfy that. So, firstly, so let me just write it like this. Let y be this y1 to ym. Okay, a composite vector, just I put them together, y1 to ym, there are m of them, and these are all greater than equal to 0, right. And they also satisfy that the sum of these yi's is equal to 1. So, this here, let us call this capital Y. This capital Y is the set of mixed strategies for the row player. So, every mixed strategy for the row player can be written in, is basically can be expressed in this form. It basically is a vector of length m. Now, the components are greater than or equal to 0 and they sum to 1. Okay. And you interpret the ith component as the probability with which the row player is going to play row I. Okay. All right. What is similarly now for the column player? Let's denote it by Z. Suppose there are n columns, then what is a mixed strategy for the column player? The mixed strategy for the column player is a vector now Z1 to Zn. These Z's are all greater than or equal to 0. These Z's are all greater than or equal to 0 and they have the property that if you sum these Zj's, they sum to 1. Let's call this as a set capital Z and this is the set of mixed strategies. For the column player. Okay. Now, if they play these strategies, okay, a strategy Y, if row player plays a strategy Y from capital Y and Z, and column player plays a strategy Z from capital Z, then they are going to now get a payoff which is going to be a random variable, because he's going to randomly choose an actual column and an actual row. He just decides the probability with which they are being chosen using capital Y, using these Y and Z. Okay. So, players decide the probabilities with which these are to be chosen, but they have to actually act a column or a row. So, which means that now the row that is chosen, so row I is going to be chosen randomly, row J is going to be chosen randomly. So, the players would get a payoff Aij, okay, when row I is chosen and row J is chosen. Now, what is the probability with which I is chosen and J is chosen? Yizj. Why? Okay, but why are they independent? Non-cooperative. The game is non-cooperative. Players cannot communicate with each other. They have to randomize independently. Right? So, because they randomize independently, see, at the end of the day, if I want to define a random payoff, I have to define for you the joint distribution of the row and column. I have only defined for you the marginal distributions, which is the probability of choosing a row and the probability of choosing a column separately. Right? Now, from the marginals, if I want to be able to generate the joint, in general, I would need some more information, but then that would also require the players to coordinate between themselves if they have to correlate their choices, right. So, since the players cannot communicate with each other, this automatically means that the choices are being made independently. Okay. So, the probability that you see row I and column J being chosen is the probability that you see row I being chosen times the probability that you see row J being chosen. Okay. So, the payoff now that the players are going to get is this random payoff. They get this payoff with this probability. Okay. Now, and then, so whenever there is a stochastic payoff involved, so there is, you can, this can be shown very formally, but essentially remember that what the player must do then is to look at the expected value. So, the expected value of this is what players have to now. This is actually the payoff that they receive. So, yeah, so there is a theory of utility from which you can show that under a set of axioms of rationality, what a player must do is maximize the expected payoff or expected utility. And in short, so whenever there is a stochastic outcome, what you need to look at is the expected value of it. You could have looked at other things, you could have looked at its variance, you could have looked at its tail probability, you could have looked at its max, etc., etc. Why should you look at its mean? Well, there is a reason for that. Yeah. Yes. 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 Yeah. Yeah. So naturally, because I have to compute the expected value there. Yeah. Okay. So in other words, let's call this something. Let's call this j of y comma z. That is equal to this. And in fact, I can write this out in more compact form, and this is just simply y transpose az. So I can think of y and z these as column vectors. Okay. So these two, capital Y and capital Z, these two, I will think of these as column vectors. Column vectors. If these are column vectors, then this sum is essentially just can be written in this sort of form. It's y transpose az. Is clear? So now what you have is a zero sum game, but where the strategies are y and z. Earlier the strategies were I and j. Now the strategies are y and z. The row player is looking to pick a distribution on the rows to minimize, to get the least expected value here, which is the least value of j. The column player is looking to pick a distribution on the columns to get the maximum value of j. Okay. It's still a zero sum game, but with these now as their strategies, the distributions as their strategies. So what the players have to do is strategically decide with what probabilities are they going to be playing each of their particular rows or row or column. So we can once again define something analogous to what we did earlier. Since this is just again a zero sum game, but in a different strategy space, I can once again talk of the same logic that I did so far. Each player is looking to make maximum damage to the other. Each player can think of the worst case damage that the other can do and try to minimize that worst case damage. Yeah. Correct. Correct. Yeah. So the strategies now are the Y's and Z's. Yes. Which conditional probability? Yes. So the players pick a distribution and play with that. That is the assumption. So the game is just played once. Just what they need to decide is the distribution. Okay. So the randomized choice is a very convenient thing because it can be applied in any situation, that interpretation of a mixed strategy. But the problem with that is also that and it also gives you a proper interpretation as a probability measure, and then you can compute expectations and so on. The problem with that is there is the way to if you want to give it an operational interpretation, like exactly how is the game played out, many people then try to think of the game being played multiple times. Okay. So if the game, but remember that is not what is being done here. We are not assuming that the game is played multiple times, and this is not the frequency with which, so yi is not the frequency with which player I chooses row I. If the game was being played multiple times, the players would also strategize in a different way, knowing that the game is going to be played in such and such way, and that leads to a different analysis altogether. It's called a repeated game. That is not what is being done here. It's not the frequency with which they are playing these strategies. It's a random choice. So you should be comfortable thinking of probability without thinking of frequency of use. Okay. So it is a random choice arising out of a sophisticated design of the probability distribution. Is this clear? So a vector y star in capital Y is a mixed security strategy for the row player if, look at his payoff, look at the worst case damage that the column player could do to him. Okay. And this here is called the mixed security level, denoted as VM of A. VM upper bar of A. And likewise, the vector Z star NZ is a mixed security strategy column player if okay. So, this is how we can define now the corresponding security strategies. So, these are security strategies in the sense of security strategy so they are in the sense of distributions. So, in terms of mixed strategies, what are the security strategies they should be playing? So, what kind of distribution gives them a certain guarantees the players a certain amount of certain payoff. That is what is being defined here. Okay. Now, so how many mixed strategies does a player have? How many mixed strategies does a player have? Infinitely many, right? Necessarily, because every distribution, probability distribution is a mixed on pure strategies is a mixed strategy, right? So, if he has at least 2 pure strategies, he will have infinitely many mixed strategies. So, the set of strategies now has become infinite. Okay, it's when you go to mixed strategies, automatically the set of strategies is now becomes infinite. So, it is actually not that straightforward to now say even that a security strategy actually exists, showing that there exists such a Y star that satisfies this particular property is itself not itself requires a proof. You need to prove that there exists a Y star which satisfies it. Earlier, all you did was, you could just checked over columns, then rows and so on, and you could immediately derive that. Now, why does there even exist a distribution like this has to be shown, a distribution that is better than all other distributions. Okay. So, that is one this thing. And so, once the question of existence is along with the question of existence, we also have therefore a question of whether mixed security levels can be thought of as well defined. All right. So, this needs some amount of work. So, this needs some analysis. You need to show that there exists actually a mixed strategy for each player. But assuming there exists one, we have the same properties that we had earlier. We have that we always have VM upper bar greater than equal to VM lower bar. This can be shown in just the same logic that we had earlier. Okay. So, we always have this particular thing. Now, we move to this particular regime of where now players are allowed to randomize, but we need to still justify what is it that is being how exactly are players gaining from randomization. Okay. So, to see how players gain from randomization, let's observe one simple property. Can you tell me what is the relation between VM upper bar and V upper bar? How are these related? Vm upper bar is smaller. Why? You are taking, okay, so that is one of the arguments that is, so Vm upper bar is, the claim is Vm upper bar is smaller than V upper bar, and the reason that is the case is because mixed strategies are more general than pure strategy, right. Pure strategy can be thought of as a mixed strategy where only particular pure strategy is given probability 1 and all other strategies are given probability 0. But is that enough? Because if you see how Vm has been defined, remember, okay, yes, the mixed strategies are more general for than the pure strategies, but you are also maximizing over now. Earlier you are doing max over j, now you are doing max over z. So the maximization is also being done over a larger set. Okay. 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 So that is, so that's where the subtlety is basically, and the answer is correct. So it is true that Vm is smaller. So in fact, I'll write out the more general thing. We of course have this thing that I have written out here, but we also have V upper bar of A is greater than equal to Vm upper bar of A is greater than equal to Vm lower bar of A, which is in turn greater than equal to V lower bar of A. Okay, and so let's actually prove one of these inequalities. So let's prove this one, for example. Okay, so I'm going to assume that a mixed security strategy exists. Okay, for the moment. So what is a mixed security strategy? It's a Y star such that Y star transpose AZ max over this is less than equal to max over Z Y transpose AZ. So actually we can only focus on the left hand side and just look at this more carefully. This Y star transpose A is a row vector multiplying with a column vector Z having components Z1 to Zn, right. Now what are these Z1 to Zn? Z1 to Zn are simply this is together a probability distribution, right. So these are all essentially some kind of weights, they add up to 1, they are all greater than equal to 0. So when you want to maximize this over Z, okay, we wanted to maximize this thing over Z, okay, we want to maximize this quantity over Z, we have to basically decide what weights should these components Z1 to Zn get. What should be the weights? Precisely. So I look at the column that has the largest value, okay, here I look at the column that has the largest value and pick that one and give that Z probability 1 and all the others probability 0, weight equal to 1 and all the others get weight 0. So this actually therefore is equal to, so the left hand side here, this is actually equal to the max over j of, or actually let me just write this for the right hand side, in fact that will make things easier for me. So I will write this for Y transpose, right. So you pick the largest column, largest value from this row vector Y transpose A, give that particular guy weight 1 and everything else 0. That has to be the maximum value over all possible weighted combinations like this. Okay. So now therefore, now you have basically the same thing that we had earlier, because this is actually now, so now minimizing this over Y in Y, minimizing the max over j of Y transpose A j this is naturally more general than minimizing over every row, because if I took because I can take y to be a pure strategy and then I would get just aij there. So, if y is a pure strategy, y transpose a j becomes equal to just the pure strategy I, let us say, then this becomes aij, right. So, that means if y is a pure strategy means what? It gives probability 1 to row I and all other rows get probability 0. Then in that case this becomes. So, therefore, this is therefore more general than minimizing over rows itself. So, consequently, the minimizing value has to be lower because you are minimizing over a larger set, right. So, minimizing over the minimum value has to be lower because the set of mixed strategies is a larger set. So, consequently, we get this inequality here, that Vm upper bar has to be less than equal to V upper bar. Same thing can be argued even on the other side, and we get that Vm lower bar is greater than equal to V lower bar. The first one, yeah, the same sort of argument as before. So, I can just show this to you. So you just have j of y comma z as this, right, and take any this is always greater than equal to the min over y in y transpose az, and it is always less than equal to the max over z in z of y transpose az. Okay. If you want, again, if you want, I can put a dash here if you are getting confused. This is always the case. And so, now what I have on the left hand side is a function of y, and I have right hand side as a function of z, function of y alone and z alone, and the left hand side is always greater than equal to the right hand side. So, which means the least value of the left hand side is greater than equal to the largest value of the right hand side. Okay. So, that and then, so the min over y max over z in z of y transpose az, this is greater than equal to max over z min over y. This here is your Vm lower bar, and this is Vm upper bar. So, actually this does not require this kind of form. In fact, you can do this for any function. Take a function of two variables, the min max is always going to be greater than equal to the max min. That holds for any function. Okay. All right. It still has the same issues still there, no? So, okay, so I do not want to take away the punchline, but essentially we still have this here, the inequality. It's no different from the inequality we started with, which was this is greater than equal to this. Okay. So, what will happen in the next class is that I will show that this is in fact equal. Okay. V bar of A not equal to, that is because there could be in general, this is certainly more general than that. Okay, all right. So, the reason for that is, okay, maybe I can just talk about that here. Yeah, so why are these not equal? So, we just showed that V upper bar is greater than equal to Vm upper bar, but then why are they not equal? The reason they are not equal is if you see this expression here, I just said that if you take y to be a pure strategy, take y to be a pure strategy I, then this just reduces to aij. Now the reason this is not the same as minimizing over pure strategies is because this now the resulting expression that you have here is not linear in y anymore. This expression here was linear in z. For a fixed y, it was linear in z. So therefore, you had to just find the weight, the coefficient with the largest coefficient and give that the full weight. Whereas if you see this here, this is not linear in y anymore. This is the max of linear functions. And the maximum of linear functions is actually the way it looks would be the maximum of linear functions. Take this function, take this function. What would be the maximum of these two? It would be this region. Up to this point, the second one is larger. After that point, the other one becomes larger. And this is now a max of several such linear functions, right? N of these linear functions. So it's not linear anymore. And because it's not linear anymore, you cannot claim that this is the same way as before. You cannot pick a component. See, because the component has now gone inside here, it's hidden inside this maximization. Even if you did pick a component, there would still be outside a max over j, which will keep switching based on what y you have chosen, the maximizing j. Right? For some y's it will be this j that is maximum, some other y's it will be this j that is maximum. Yes. So okay. So that is, I was going to show that next time, but actually, so what you are asking is this equal? Is this going to be strict in general, right? Yes. So there you can show many functions for which this is the case. Okay. But this is already telling us one justification for moving to mixed strategies. The randomization has benefited both players. Each player has improved his security level by randomization, right? Is pure strategies, yeah. No. So that's where this is subtle. So we'll again, we're jumping ahead a little bit. But for the moment, let us just justify why it makes sense to allow players the option to randomize. It's because by randomization they are, you cannot, once their security levels have improved, you cannot basically deny them that option. Essentially, they have the once security level improves, which means that if they could, they would randomize. Okay, all right. So what I'll show next time is basically the champion theorem here, which is that this is equal. Okay, so all the things that we were fantasizing about that would happen if V upper bar is equal to V lower bar would now happen for free, because V upper bar and Vm upper bar would be equal to V lower bar. Okay. So there will always be a saddle point, etc., etc. All those consequences will follow, but in the space of mixed strategies, not in the space of pure strategies. Okay, all right.